Hey guys, it's Off1 here, and today we're going to be solving Alien Dictionary. So I'm sure you can see that the interface is a bit different, and that is because I don't have Leetcode Premium, so I'm solving this problem on a website called Leetcode. The only difference for this problem is that they have extra requirements here, number 4 and 5, but we can just ignore them for now because they're not really important. So this is a Leetcode hard problem, but once you actually look at the problem, it's not that hard. I think the hardest part is actually trying to read the problem and dissect what they want. So let's do that. So we're told that there's a new alien language which uses the Latin alphabet. And this part right here is irrelevant, so I'm just going to cross it out. Next, we're told that the order among the letters are unknown to us. So that means that instead of our alphabet going A, B, C, D, we don't know the actual order of this alphabet here, and that's what they're asking us to find. And in order to help us find the order, we're giving a dictionary here that is guaranteed to be not empty, so we don't have to worry about that edge case. And we're told that the words in a dictionary are sorted lexicographically by the rules of the new language. And all this word means is that, let's go back to our English language. If we look at our dictionary, we're going to see the word R come before the word art. The reason is because E comes before the letter T in our English alphabet. So for example, we can have, let's say this was a word. The dictionary will be in this order because E comes before T and T comes before Z. So now that we understand this part, let's look at this alien dictionary and see what their relationship is. So we have the word WRT and WRF. And for this language, we can assume that T comes before F because that is the way it's sorted in this dictionary here. And that's what lexicographically means. So basically all this means is that the words in the dictionary are sorted the same way that it would be in a regular dictionary. Okay, so now that we understand that, let's take a look at these three statements here. So first, they tell us that we can assume that all letters are lowercase. So that's good because we don't have to worry about any uppercase or lowercase distinctions. And next, they tell us that the dictionary is invalid if string A is a prefix of string B and B is appearing before A. And I think this was just a mistranslation because Leetcode is a Chinese website. And I think what they mean here is, let's say we have the word apes. If the next word in the dictionary is ape, then the dictionary is invalid, because in a regular dictionary, apes would come after ape. So if you have an invalid dictionary, then that means we have to return an empty string, because that means there's no actual way to derive the order of the language. Okay, so now let's take a look at these two requirements here. And to be honest with you, I have no idea what number 5 means, so we can just ignore that. If anybody knows, just leave it in the comments below, but I couldn't figure it out, and it doesn't really seem to affect the solution. But number 4 does, and we're told that there may be multiple valid orders of letters. So for example, let's say we know that T comes before F, and we also know that E comes before D, but we don't know which one of these comes first or in between. So for example, our order could be E, T, F, D, or it could be T, E, D, F. We don't know. And we're told here for Leetcode to return the smallest in normal lexicographical order. So that would mean we would want to return the alphabetical version of it in the English language. On Leetcode, I'm pretty sure they say you can return any combination, so I'm going to approach the problem like that, and when we get to the code, I'll show you how to fix this part. So I know that was a lot of explaining, but I think if you understand what the problem is really asking, then this problem goes from a hard to a medium. So here I've redrawn the problem from the example, and we're just going to solve it by hand. So how do we know what letter comes before which letter in the alphabet? Well, if you remember our English alphabet, we know that R comes before art in the dictionary. And because of this, we know that the letter E comes before the letter T because of the way it's sorted. So if we apply that principle to this example here, let's take a look at our WRT and WRF. Well, now we know that the letter T is supposed to come before the letter F in this alphabet. So we can start a graph. And the reason we're using a graph is because we want to know relationships. And normally when you want to figure out some kind of relationship in a problem, you're going to use a graph. So let's put T in the node and make it point to F. So that way when we traverse the graph, we start at T and we can map that in our output, and then we can go to its neighbors and we can see that F is supposed to come afterwards. Okay, so now we have this relationship here. So now let's go to our next two words. We're done with WRT, so now let's compare WRF and ER. What we're going to do is look at the first letter that's distinct between these two, and we can see that W and E are the first distinct letters. So we know that W comes before E. So we're going to map W to E. So the current relationship between the letters is W comes before E and T comes before F, but we don't know anything else. We don't know if E connects to T or if any other relationship happens here. Okay, so now let's look at our next word. So now we're going to compare ER to ETT. So now let's see. The first characters are the same, so that doesn't tell us anything new. And now we have R, and that comes before T. So what we can do is say R comes before T. But as you can see, we already have a T node up here. So we can actually just put this R before the T. So now this is our current graph. We have two different graphs that tell us R comes before T and T comes before F, and then W comes before E. So now let's take a look at these last two words here. So if we take a look at the first distinct character, so let's see, we start at the first character, and we already see that E is different than R, and what we can assume here is that E comes before R. So now we can map E and say it comes before R. But as you can see, we already have an E here and an R, so we can actually just connect these two graphs here like this. The final step is just to output this as a string. So our output has to be WERTF because that is a valid order. So we have to somehow traverse this graph and get this output. And there's two ways to traverse this graph. You can use DFS or you can use BFS. And I'm going to be using DFS because I feel like it's simpler. With BFS, there's a lot of extra stuff you have to do, and I don't feel like doing that. I want to keep this code as nice and simple as possible so you guys can understand it. The only problem with doing a DFS solution is that if we do DFS starting from here and print out the output, we're going to go all the way down to the very bottom and see this F here. So we're going to print out our F first, and then we pop back up to T. So we print out T, and then we do R, E, and W. So our output would be this, which is just the reverse version of this. So in the end, before returning, we can just reverse this string, and then DFS works just fine. And this is also a cycle detection problem. So for example, if we had WF here, then our E would also connect to the W. And if we do DFS, we're going to end up going in a loop. So to detect that, we have to keep track of what nodes we have visited so far. So let's say we start at W, we will mark that as visited. And then we go to E, and then we mark that as visited. When we go back to W, we're going to see that we already visited it in our current DFS call, and we can just return that as an invalid dictionary. And that's basically it for this problem. So basically, this problem just breaks down to a DFS and cycle detection problem. And there are a few other edge cases. For example, W can connect to F, and this will be taken care of in the DFS call by itself. We don't have to do anything special for that. So now let's discuss the time complexity. The time complexity depends on the number of words we have and the characters in each word. So for example, our worst case could be that we visit every single character in every single word. So we can say that the time is O of C, where C is the number of letters in every word. Our space complexity would be O of V plus E, where V is the number of nodes we have and E is the number of edges. So now that we know that, let's get into the code. So first I'm going to separate the problem into different parts so it's easier to follow. So the first thing we're going to do is make the graph. Then we're going to populate the graph. Next, we're going to write our DFS function. And then at the end, we can iterate through our graph using our DFS. And then at the end, we can just return our result. So what we're going to do is create a character graph. And what we're going to do is initialize a empty hash map. And our goal is going to be to have our hash map look like this. So we're going to have our character, let's say we are at B first, and that's going to be mapped to the characters that come after it. So for example, let's say A comes after it, and also C comes after it. So our map would look something like this, where we map our character to an array of characters that come after it. So we're going to do for every word in words, and for every character in that word, what we're going to do is initialize our character graph at the key C, and give it an empty array. The next thing we're going to do is populate our graph. And the way we populate the graph is by taking word 1 and word 2 and seeing which character is different. And then whatever character is different from word 1 goes into the key, and the character that is different from word 2 comes after it. For example, we would have A, and that would be mapped to B in our English letters. So we're going to do for I in range of the length of words minus 1. The reason we're doing minus 1 is because we're going to be looking at the word afterwards, and to not get an out of range error, we need to do a minus 1. And you'll see why in a second. So let's say word 1 is equal to words at I, and word 2 is equal to words at I plus 1. So this is why we're doing the length of words minus 1. From here, we're going to find our minimum length because we don't want to go out of bounds. So we only want to look through as many characters as there are in the smallest string. So we're going to do min length is equal to the min between the length of the words. And then from here, we can iterate through every single character and see which one is different. So we're going to do for j in range of min length, because that is the length of the smallest word. We're going to check if word 1 at j does not equal word 2 at j, then that means they are different. And if they're different, then we want to add them to our hash map. So we're going to do character graph at the key word 1 at index j, and then we're going to append our word 2 character to it. So for example, if we had ape and art, then our key would be p, and we're going to put r as its neighbor. And if we find a character that doesn't match, then that means we can just break this loop. So we're almost done populating the graph. We just have to take care of the one edge case where, let's say word 1 is apes and word 2 is ape. Then that means the dictionary is invalid because ape should not come before ape. And to do that, we just want to check if the length of word 1 is greater than the length of word 2 and the prefixes are the same. So we would have word 1 from the beginning all the way up to the min length, and that should equal word 2 from the beginning all the way up to min length. So that means we have the same initial letters and word 1 is still bigger. If that's the case, we just return an empty string. Okay, so at this point we have made our graph and we have populated the graph. So now we can just iterate through the graph, and then afterwards we can come back to our DFS and make that function. So to iterate through the graph, we just want to iterate for every character in our character graph, and we just want to do our DFS function. And I'm going to be calling our DFS function isCycle because that's what we're looking for. So we're going to check if the graph is a cycle, then we want to return an empty string, because that means we found a cycle and that wouldn't be a valid dictionary. So now let's write our DFS function. Before we write the DFS function, we want to initialize two things. First, we want to have a hash map, and in this hash map we're going to keep track of our visited nodes. And we also want to create a result array. And in this result array, we're going to just store the letters we visit and then reverse them at the end. So before we return the result, we want to reverse the array. And then at the end, we can just convert our array to a string. And the way to do that is by returning an empty string, and then we join it with our result array. So now all we have to do is make our DFS function. So we're going to define isCycle, and we're going to be passing in a character. And from there, we want to check if we visited this character. So if our character is in our visited set, then that means we already visited it, and we can just return whatever is stored in that value. So we can return visited at the key C. So that way, we don't have to do repeated work. If we already visited a cell, then we already know that there's either is a loop or there's not a loop at that point. And the way we can break up this DFS call to make it make more sense is going to be our check. And if we pass our check, then we can mark our node as visited. And after we do that, we can just call DFS again on the remaining neighbors. So we're going to do visited at the key C is now true because we're visiting it currently. And now we want to do our DFS for all the neighbors. We're going to do for neighbor in our character graph at the key C. So that means all the letters that come after it. We want to iterate through those and create a graph. And we want to check if those are a cycle as well. So if isCycle for our neighbor, then that means we can return true here because that would be a cycle. And if it's not a cycle, we can just mark our node as not visited now because our DFS would be over. And then at the end, we can just append whatever character we're visiting to our array and return false down here because we did not find a cycle. And that's our whole code. And this would work on Leetcode, but the problem is that on Leetcode, you can't just blindly iterate through the character graph. You have to sort it by the keys. So we're going to do character graph sorted by the keys. And we also have to reverse it. The reason we do this is because they want us to return it lexicographically, which means they want us to return it in English alphabetical order for some reason. But either way, for Leetcode, you don't need this part. You can just iterate through the character graph and that should work. But just so you can see that it works on Leetcode, I'm going to submit it now. And as you can see, the solution is very fast and efficient. And now I'll go through the code manually. So because the code is huge, I can't go through the whole code for every single word. So I'm just going to give you the main idea from each block. So the first thing we're doing is making a graph. And what we're doing is actually just making a hash map and giving every character an empty array. So all it looks like is like this. For example, let's say we have W, R, and T. All of these would be mapped to an empty array. From here, we would populate the graph. So let's just take the first two words here, WRT and WRF. We would check if these are valid dictionary entries, and that's what this if block does here. So for example, I mentioned it before, but if we had apes and ape in this order, then that means this would be an invalid dictionary because the word apes cannot come before the word ape. But that's not the case here. These are valid dictionary entries. So from here, we would iterate through every character in the smallest word. And as soon as we find a different character, then we want to append the different character from word 2 onto the word 1 key. So for example here, we have W and W, these are the same, R and R are the same, and then you have T and F. So now, we're going to map F as the letter that comes after T, so this would be in the array here. So here I've just populated the map, but there is one difference compared to the normal example, where F has a neighbor W. So this graph here, instead of just being one direct line, F now connects back to W. And the reason I'm doing that is to show you what isCycle does. So here I've drawn a visited hash map, and now let's do our DFS. So let's say we started this W here just to keep things simple. So we start at W, and we check if it's in our visited set. Well, it's not. So we can go onto here and mark it as true, that we have visited it. And now we go through every neighbor for W, and the only neighbor is E. So now we're at E, and we do the same thing. We check if it's in our set, and it's not. So we mark it as true. And we do that all the way through R, T, and F. So now R is true, T is true, and now we have F. So once we go in our cycle, we see that it's not in our set, so we can mark it as true. And now, when you visit all the neighbors for F, we're going to see that we're going to go back to W. And now our C is going to be equal to W, and we check if C is in our visited set. And we see that W is, and we're going to return true here. And once we return true there, this is going to return true. So that means this if statement here is going to get triggered and we're going to get an empty string. And that's how I detect a cycle. So now let's say it's not a cycle and we start doing DFS at W. Well, what we're going to do there, just go to the deepest node and then add that to the result array. So we're going to add F to our result array. We're going to have F, and then we're going to put T, R, E, and W. And then from here, we're going to reverse our array. So we're going to have W, E, R, T, F. And we're going to convert it to a string down here, and this would be our final result, and this would be correct. If this video helped you in any way, please leave a like and subscribe. Thanks for watching, and I'll see you in the next video.